9.3, the intersection of two planes. So now what we're going to focus on is, of course, intersection of two planes. There are three possible cases. Okay, so case one is infinite solutions intersect along a line, okay, specifically a line. So what happens is the planes cut each other and then they intersect along this line. And of course, every point on the line is a point of intersection. So we just state the line as the entire, like, line of intersection. Okay, line of intersection. Okay, case two, zero solutions. So these planes are parallel and non-coincident. So they do not lie on top of one another. Okay, they're parallel and have a different d value. And then case three, infinite solutions. So this is called a plane of intersection. So the entire plane itself intersects, like, so plane one intersects plane two, and this is when the d's are equal. Okay, so they have either the same normals or the same direction vectors, that's fine, and then the d's are also the same. So no, it's not possible for two planes to intersect at a single point. This does not make sense. It's either zero, a line, or an entire plane. So let's take a look. Okay, example one, determine the solution to the system of equations for these two planes. And then what we're going to do is we're going to discuss how they're related to one another. Okay, so if we took these two planes, I'm going to put these in a matrix. 1, negative 1, 1 equals 4. And then 1, negative 1, 1 equals 5. Okay, so if we were to actually do elementary operations on these, we could take row 2 and subtract row 1. So row 1 wouldn't change. So 1 minus 1 is 0. Negative 1 minus negative 1 is 0. 1 minus 1 is 0. 5 minus 4 is 1. This is what we would get. Okay, so before we even touch on this, let's actually just take a look at these. 1 and 1, negative 1, negative 1, 1 and 1. Okay, so we know that the normal from equation 1 equals the normal from equation 2. Okay, what's different is the d value. So the d value in equation 1 does not equal the d value in equation 2. Okay, so this is what's important in this example. And what this allows us to get is 0, 0, 0 equals 1. So what this says in my mind is that 0x plus 0y plus 0z equals 1, which doesn't make sense because we can't multiply a bunch of stuff by 0 and it equal 1. So simply put, because there are no values of x, y, and z that can satisfy this, therefore there is no intersection. I don't want to say point of intersection because two planes will never intersect at a point. It's either going to be a line or plane or no intersection. So I'm just going to write no intersection. Okay, so I showed you that algebraically. I showed you it simply using the normals, and I will continue to show you the both methods. Okay, example 2, determine the solution to the following system of equations. So same idea. So if we want, we can write normal 1 beside, which is 1, 2, negative 3. Okay, and normal 2, which is 4, 8, negative 12. 4, 8, negative 12. So if we actually take a look at this, 1 times 4 is 4, 2 times 4 is 8, negative 3 times 4 is negative 12. Normal 1 is 4 times normal 1 equals normal 2. So they are like duplicates of one another. So now let's actually test just the d values. So we have d1 is negative, actually it'd be positive 1 because when we write the d value, we write it in the Cartesian form. We'll leave the negative 1 on the right hand side, but just know that it's positive 1. And then d2 is positive 4. So if we think about it, 4 times d1 equals d2. That to me means that these are the exact same equations. Already, I know that there's infinitely many solutions. Infinite, let's not call it, let's call it the plane. Okay, so we'll call that the plane of intersection. And we can call the plane of intersection just x plus 2y minus 3z equals -1, because it's going to intersect that entire plane. Or you could have like mentioned the second plane, which is totally fine because they're equivalent. Okay, I'm going to show you elementary operations. 1, 2, -3, -1, 4, 8, -12, -4. So if we took these and we did row 2 minus 4 of row 1, what this is going to look like is 0, 0, 0, 0. When we get this situation, we know that we have 0z equals 0. So what value of z, or even 0x plus 0y plus 0z equals 0? So what value of x, y, and z are going to satisfy this? Okay, in other words, okay, so therefore, how we do this is it's a little bit different, okay? So we need to sub in two parameters for 0 for the y and the z values. So let's just say y has the parameter of s, such that s is an element of the real number system, and z has a parameter of t such that t is an element of the real number system. So our plane of intersection, where this is going to intersect, is x plus, instead of writing 2y, we're going to put 2s plus, minus 3z, right? And we get that from here, equals -1. So what we have here is, instead of writing the plane of intersection as one of the planes that we have, we can write it in parametric form. We can write it as x equals -1 minus 2s plus 3t, y equals s, and z equals t. So we can write either one. This one is going to be probably just more accurate. Okay, a little bit like one step further, where you're subbing in parameters for y and z. So any parameter for y and z, and then x is -1 minus 2 of the s parameter plus 3 of the t parameter. So every point that lies on this plane here is the solution to this linear, or this system of equations. All right. Intersection of two planes and their normals. So if two planes, so like pi1 and pi2, have normals n1 and n2, we know the following. If the normals are scalar multiples of one another, then the planes are coincident and they have an infinite number of points of intersection, or the planes are parallel and non-coincident. So coincident is parallel and the same, basically. Okay, or the planes are parallel and non-coincident, and there are no points of intersection. So this is like parallel and distinct. Okay, or if n1 is not a multiple of n2, so the normals are non-multiples of one another, then simply the planes intersect in a line. Okay, and we saw that diagram here. When it went like this, and then they intersected in a line. Okay, so let's go ahead and determine the solution to the following system of equations. So for this one, we can go ahead and write the normal, and we can just assess the normals at first. Okay, 1, -1, 1. 2, 2, -2. Okay. So these are not multiples of one another. Okay, you can see that normal 1 times 2 gives you approximately normal 2. However, the issue is that the negative signs are on different components. So they're actually not multiples of one another. So n1 is not a multiple of n2. In this, we don't even have to test the d's. We go straight to actually finding the line of intersection. Okay, so 1, -1, 1, then we have 3. Okay, and just put everything in a matrix right now. Okay, so let's get, as best we can, let's get zeros in this bottom left corner, okay? So I'll rewrite 1, -1, 1, and 3. And we probably don't even need to touch that, but let's go ahead and do row 2 minus 2 of row 1. So 2 minus 2 is 0. 2 minus -2 is 4. And -2 minus 2 is -4. And then we have 3 minus 6 is -3. Okay, and this is all we can break this down to. I'm going to show you why, because this right here, this 0, what this shows us is that if we were to subtract a multiple of row 1 by row 2 or vice versa, we're always going to be able to get that 1, 0. However, this 0 may turn into a number, and then we would just have a 0 in like the y as the y component, or the 0 as the z component. But never again will we be able to get more than 1 0 there. Okay, so let's work with this. Okay, so what we have here, I write this in blue. Okay, we have x minus y plus z equals 3, and then we have 4y minus 4z equals -3. Okay, so what we want to do, we want to write parametric equations, okay? So this z, because we have a y and a z, what we have to do for that z is we're going to sub in a parameter. So let's say z equals t. Okay, so we have the parameter. Now, I'm going to bring this over. Okay, so now let's sub in z equals t. So we have 4y minus 4t equals -3. And let's just isolate for y. This is going to represent the parametric equation for y, but we have to get y by itself. We get -3 plus 4t, and then we're going to divide both sides by 4. So here is the parametric equation for y. Okay, now let's find the parametric equation for x. We have x minus y, which is -3 over 4, plus, we can do this as t, 1t, plus z, which is just t, equals 3. So x plus 3 over 4 minus t plus t equals 3. Well, those cancel out. That makes it convenient. We get x equals 3 minus 3/4. In other words, 12 over 4 minus 3 over 4, I get x equals 9 over 4. Okay, I'm just going to change the color so this can be distinct. Okay, therefore, we have a line of intersection. So whenever we have 1, 0 in the corner, and then like we have to sub in one parameter, we're going to get a line of intersection. Therefore, line of intersection, x equals 9 over 4, y equals -3 over 4 plus t, and then z equals t, and those are the parametric equations for the line of intersection. Okay, example 4. Determine the solution to the following system of equations. So I'm going to write the normals out first, 2, -1, 3, and then normal 2. Just take note of this. There's no y component here, so it's 2, 0, and -3. Okay, normal 1 is not a multiple of normal 2, so we don't even have to check the d's. We just sub it straight into a matrix E. Okay, so we have 1, 0, -3, 1. Okay, if you've already noticed, there is a 0 in here for the y already. So what we can do is we can just skip all these steps because we're not going to be able to find another 0. Okay, if we add a multiple of row 1 to row 2, or even subtract a multiple of row 1 to row 2, we're going to now get a number in this position, and then maybe get a 0 on the x or a 0 on the y, but it's going to be equivalent. So what we're going to do now is just approach this question. So instead of having a 0 in like the first box, which we're used to, we're just going to simply have a 0 in the second box, okay, which we saw in the last example, example 3. So if you recall from the last question, what we had in this row 2 was it looked like 0, number, number, okay, and then number. So all we did is substitute in z equals a parameter. So we're going to do this exact same thing here. We just want to make sure that you don't sub in the y component equals a parameter, okay, because y equals 0. So all we're going to do is substitute z equals, let's say, t. Okay, so z equals t. Let's take this equation, which I don't even have to rewrite these equations because I didn't really do anything with them. We can just take the originals. So we'll write x minus 3t equals 1, bring that over, x equals 1 plus 3t. So we have the parametric equations for the x and the z. All we're missing now is the y. So we keep moving up, okay? So 2x minus y plus 3z equals negative 2. Let's expand and simplify. 2 plus 6t minus y plus 3t equals negative 2. We have 6t and 3t, which is 9t. We'll leave the negative y. And then we'll bring that 2 over. Negative 2 minus 2 is negative 4. Okay, so I get y equals, bring this over, I got negative 4 minus 9t, but then we'd have to divide out that negative 1, so we just negate each term. 4 plus 9t. So therefore, the line of intersection is x equals 1 plus 3t, y equals 4 plus 9t, and then z equals t. That's the line of intersection of these two planes. An equation of a line that passes through this point and is parallel to the line of intersection of these two planes. Okay, so these two planes, I'm going to write their normals first. I'm going to write 1, 2, and negative 1, and I'm going to go ahead and write 0, 1, and 2. Okay, so if we had two planes like this, and we had their line of intersection, I'm going to just embellish it, line of intersection. What we know about this line of intersection is that it's going to be perpendicular to both planes, or both normals. Okay, normal 1 and normal 2. So we can go ahead and dot this, or sorry, cross it. So we're going to have n1 cross n2. 1, 2, negative 1, 1, 2, negative 1. 1, 0, 1, 2, 0, 1, 2. So we're going to go 4 minus negative 1, comma, 0 minus 2, 1 minus 0. Okay, so I get 5, negative 2, 1. This is going to be our direction vector of our line. Okay, so now it's actually pretty easy. Our line is going to be in the form 5, negative 2, 3, because that's a point that it goes through, and then plus some parameter, 5, negative 2, 1 as the direction vector, and we know t is an element of the real number system. Okay, I'm going to show you another method to do this, okay? Okay, another method of solving this is to simply find the parametric equations of the line of intersection of these two planes. So starting from this, we know that we can sub in z equals 0. Okay, because remember in the last line of this matrix, it's going to be 0, 1, 2, 1. Okay, so z equals 0, and then we can solve for y. Y equals 1 minus 2t. Oh, sorry, z equals t. Okay, and then for the x value, we can write x plus 2y minus t equals 6. Expand x plus 2 minus 4t minus t equals 6 minus 2. And that's a negative 5t, x equals 4. If this is negative 5t, bring it over, plus 5t. Okay, so the intersection of the line of intersection is x equals 4 plus 5t, y equals 1 minus 2t, and z equals t, which gives us the direction vector 5, negative 2, 1, which is the exact same direction vector as here, and then we could just simply sub it into either the vector form of the equations, or we can put it in the corner here, x equals, y equals, z equals as parametric equations, the point 5, negative 2, 3, plus 5t minus 2t plus 1t, where t is an element of the real number system. Okay, so two a little bit different approaches, but you're going to arrive at the exact same answer.